Thank you very much, and thanks for having me here. It's a great pleasure to talk in this institute. As Walid mentioned, I'm Mohammed. I'm a PhD student at Columbia. This talk is primarily a kind of brief explanation of what I did with my advisor, Michael Collins, but some parts of the talk are also a joint work with my other colleagues at Columbia and George Washington University. So, because I hide so many details in this talk, and like if you're interested in some parts of the talk, I really encourage you to read the papers. Actually, the third paper is not published yet because of some like editorial stuff, but hopefully in a month you can see that in the Journal of Machine Translation. So first of all, I will start with a brief introduction of the problem, why this problem looks interesting and challenging to us, and then I will talk about annotation transfer and this notion of annotation transfer, and finally, very briefly, I will talk about the work that I'm currently focusing on. So, there are different levels of representation. What I mean by representation is linguistic representation or linguistic structure that are important for natural language processing and many other downstream tasks. For example, on the left-hand side, you see a very simple English sentence and different structural annotations for that sentence. For example, the very first annotation is part with speech tags. It kind of gives us this flexibility to categorize words and kind of abstract them some ways, and can be good in search systems and also in other NLP tasks as a intermediate feature. Also, like noun phrase and verb phrase information are really interesting. For example, if you're interested in nouns or like verb phrases, here like makes and repairs is a verb phrase, or like jet and jeans is a noun phrase. The other level of representation is dependency structure, where we can capture and recover the objects, subjects, conjunctions, on all these interesting syntactic phenomena happening in sentences, and also semantic role labels. I could just expand this to tons of different linguistic representations, but that's just for a brief introduction to kind of natural language problems. On the right-hand side is a simple hierarchical representation of sentiment of a sentence. You see that the part like that amazing game, I showed the positive sentiment with the green emojis. So like amazing, these kind of things are positive, but just a negation flipped the whole sentiment of the sentence. So sentiment analysis is really important, especially in social media analysis. And there was a considerable amount of work on improving performance of them. Like, for example, in dependency parsing, it's been more than, I can say, 17 years of work just on dependency parsing. And I just calculated the state-of-the-art performance of natural language processing systems in 4 tasks on the English data set on Wall Street Journal text, which is a news text. We see that for simpler tasks, like the top graph is a part of speech accuracy. It started with log linear model. If you remember all these max entropy models, it was like deep learning at the time. It started with like 96% of accuracy, and now with the CRF, deep CRF models, in English we can have like 97.5% of accuracy. While for dependency parsing, the improvement was more noticeable because dependency parsing is a more complicated task to solve. Here we see that with support vector machines from 2000 and shift-reduced parsing, it go all the way to 2013 with 93% of accuracy. And with the bi-LSTMs and all this fancy stuff in deep learning, we now can have up to 96% of dependency accuracy in English. The same thing applies for named entity recognition, starting with maxent models to deep CRFs, and also semantic role labeling started with sparse feature representations and some log linear model to a bi-LSTM based representation. So that's interesting. So we could make things better compared to like 10 or 15 years ago. So that's a good indicator for us that we are kind of solving something in NLP. But the question is, how about other languages? And what I mean by other languages, I don't mean German, Spanish, French, because for these things we also have good models. I'm talking about 7,000 languages in the world. So for these kind of languages, if we want some ideal setting, what we really need is the same data sets that we have in English in those languages, such as Wall Street Journal, Prop Bank, Brown Corpus, Attis Corpus, Switchboard, WordNet, VerbNet, and so on and so forth. And it might look very easy for us in the first site. We can just hire Mechanical Turkers in Amazon and just pay them some small amount of money and they can annotate for us. But that doesn't happen in many NLP tasks. So from my experience on Persian tree banking, it's published in NACL 13, it just took 1 year of working with 2 linguists, native speakers of Persian, to just design schema for annotation. And it was before this movement of universal annotation. So for every language, every group had to come up with their annotation guidelines. And if you actually talk with linguists, they might not agree with the universal annotation because it doesn't really focus on specific and peculiar structures in languages. And it took, the whole dependency annotation took 1 year of annotating with 14 annotators. All of them were expert in linguistics and all of them were native speakers. So bunch of money, a long amount of time, and also it was just one task in NLP for one language out of 7,000 languages. So practically speaking, we can't really put too much budget for solving NLP problems just by annotation. So you might say, okay, it's not a problem. Unsupervised learning is really good. We can work on unsupervised learning. We don't need annotated data. Actually, I was initially interested in unsupervised learning, all these EM, deep sampling, all these Bayesian models. But I just noticed that there is a problem. The more models get improvement on accuracy, the more complicated they become, and at the same time, the gap from the best, unsupervised model to the current best supervised model in English for example, dependency parsing, is about 30% absolute difference. And this means that going from a practical toolkit to a completely irrelevant toolkit. It's good, interesting for computational reasons, for knowing how human beings can understand language from raw text, but practically speaking, it's still immature and doesn't really work well. And actually, this 66% might look good, but in other languages, the state-of-the-art results are somehow around 40% of accuracy. So it's not really reliable at all. One kind of alternative approach is called annotation transfer, and generally speaking, we can divide annotation transfer in 2 categories. The first is for the time that we have a bunch of translation data, so we can project supervised annotation from language LS as a source language to language LT through word alignments and sometimes just sentence alignments. This is called annotation projection. The other way is for the time that we don't have enough translation data, so instead we can directly train on source language annotations L1 to L1 to LM and apply the model that's trained on those languages to the target language. It looks a little bit magical, but there are some ways to make these direct transfer models work. And that's where my research started, to make use of annotation transfer in both methods and see how can we help reduce the need for manual annotation for NLP systems. So what annotation projection is a kind of very intuitive. Here I just depicted 2 sentences. They are translations of each other. They're actual sentences from the European Parliament data. And we kind of collect tons of these sentences, and we do automatic word alignment on this. So the reason that I created dashed links between words is that it is automatic. It is unsupervised. So there might be errors in them. So here we see that, for example, the word political is connected to its meaning in German and so on. Here I'm assuming that German is my unsupervised language. Then we do supervised parsing or supervised labeling on the source side. I I just remove the labels, but I'm actually doing label dependency parsing. And then we project them through these alignment links. So what happens is that we assume that these projected dependencies are gold for us. We can rely on them, and we can train models on them. OK, solved. Problem is solved. Let's wrap up. But there is a problem here. I just picked a completely random sentence from the Bible data from English to Persian, my native language. Here I wrote the sentence from left to right, though Persian is written from right to left, just because to show it very clearly. And the dependency annotation on the Persian side is automatic. It's from projection. But there are certain problems happening in this particular example. One problem is missing alignments. The highlighted words are the words that don't have any corresponding alignment from the English side, meaning that there will be orphans. They won't have any dependency annotation at the final stage. The other problem is lack of lexical translation. We can have, like determiners in English are happening very frequently, while we barely have any determiners in the Persian language. So if you can think the other way, if you can think of Persian as a supervised language, kind of projecting to some other languages, Persian doesn't have a determiner, so we can't really project any determiner information from Persian to the other languages. The other problem is lack of lexical translation and idiomatic translations. The word continually in English is translated to the phrase gun in Persian, which is completely idiomatic, but it's correct. The other problem is that we use a supervised parser in English, which is not 100% accurate. So it failed to recover the structure for the phrase of the 150 days. It should be the case that days should be the head of 150, but it doesn't occur here. So all these red links shows that we're just making errors. And finally, we will have, with all these problems, we will have a partial erroneous projection for the target language. And that happens very frequently. So if you just calculate the projected dependencies, it's less than 70% accurate. When we train on something that is completely gold standard, we get 70, 80, 90. But when we train on something that's already 70, what can we expect from? But there is something that's really interesting to us, which is that for the subphrases that are kind of all having correct projections, it kind of shows it's kind of an indication of lexical translation. And that's actually how we dealt with this problem, saying that, okay, there are linguistic differences, there is translation shift, but the thing is that there is this cue that the more dense a projection is, the more reliable is that, meaning that Giza++ or whatever word alignment system is able to recover the correct alignment, meaning that it's lexical translation, not idiomatic translation. So what we did was to come up with this notion of dense structures, and we kind of decompose that to two kind of trees, full trees and dense partial trees. And what we mean by full trees is actually a scenario where when we have a source sentence and the annotation from source sentence, when it's projected to the target sentence, we will have a full projection here. So we can train any kind of parser without any problem on this. And when I kind of gathered statistical, statistics about match with a supervised parser on the target language, it's a very good indication that the more dense we have, the more accuracy we can expect from the projection. The other one is for the scenarios where we have at least 80% of the words in the target language with a projection. Here, the highlighted words are the words that don't have a projection, so it creates a partial tree for us, but we still have sentences, dependency structures in the sentence that are preserved, so we can have at least 80% of the information. So it's still good for us. It kind of means that, let's say we have a sentence that like at least 80% of the structure is lexical translation, but 20% is not. So still 80% is important to us. The other way is that, let's say we have a sentence that, the whole structure is not lexical translation, but there is a span, a local contiguous span in the sentence that if we just look at it, we have all projections for that span, meaning that we can have a span that is a lexical translation for us. Here we see that the highlighted green words are words that all have dependencies. They are contiguous. So we can say that it's P greater than or equal to 6, which means that there is at least 6 words in a contiguous span in the sentence that have projected dependency. So what can we do with these structures? The full trees, 80% dense, a span of size k. What we do is just we come up with definition that, well, the full trees are the most important and the most reliable trees for us. So let's first train a model on them. So we can come up with a just initial model to start our self-training process. What we do is we gradually decrease density. We start with the denser partial trees, I mean A1, which means that we can have spans of size 7 or like 80% of words. Then we can go to 5 and then 1. So just remember that the dense structures are a subset of the partial structures, non-dense structures. The C decode function is that when we have a trained model and we have a partial tree, we use a trained model to fill in the missing dependency of the partial tree. So here we don't really manipulate the projections. We rely on the projections, but we fill in the partial trees. And for some cases, the number of sentences that are projected is too much that we don't really get too much gain out of it. So we just select the highest scoring trees. We pick 200,000 sentences from projections. And when we pick these sentences, we add them to the full trees. So full trees is always part of our training data. We yet train another model with it. And after 3 steps of decreasing the density of the structures, we finally return our final model. And this final model can be used to parse sentences in the target language. And what we did was to experiment on 7 European languages. At that time, this was the kind of only data set that we could have from the Google Universal Tree Bank. We only use English as our source language, and other languages were also source and target depending on the setting. We use Giza++. It's a word alignment system based on the expectation maximization algorithm. And we use the Yara parser. It's a parser that I re-implemented. It's based on beam decoding and shift-reduce parsing. So there were 2 scenarios that we had. The first scenario is just having just English as our training data. The second scenario is where, for example, for the European Parliament data, all sentences, for all languages, we have a sentence. So one sentence in one language is translated to more than 1 other languages. So we can do a voting here. So here's an example of a projection where the arcs, the numbers on top of arcs, shows the number of votes for projection. 4 here means that there are 4 languages that vote for having bit to have a punctuation dependency. So the dashed dependencies are the dependencies that they were removed because they didn't get the high vote. And we use the maximum spanning tree algorithm to recover the best tree structure. And for the ones that didn't have any votes, we still didn't have anything, so it got 0. So here's a depiction of comparison with the state-of-the-art models at the time. The 3 left-hand side models are, the first one is from McDonald et al. It's a Google work. It's a kind of seminal work on annotation projection. The second one is by Zhang and Barzilai from MIT. It's a direct transfer model with cross-lingual representations. The third one is from Ma and Shah from UW. It's a annotation projection model with CRF and a maximum spanning tree algorithm. The 2 right-hand side bars, the first one is the upper bound for the state-of-the-art model. If we had a supervised first-order MSD on the 6 languages, on average, we could get 84.29. And the last one is the parser's accuracy, my parser's accuracy that I used through this research. The interesting fact is that if I just only train on full trees, I'm already better than the 2 models in the state-of-the-art. So meaning that instead of relying on everything, if we just rely on a small set which is full tree projections, we can get very good accuracies. And if we go through the whole pipeline of self-training, we get 2.2% absolute improvement on all languages. And in per language analysis, in all languages, we got improvement. Depending on the language, the amount of improvement varies. And if we apply voting, meaning that we have more than one source language, we get 5% improvement, showing that we're very close to a first-order supervised parser and kind of close to a supervised shift-reduced parser. And in parsing, accuracies more than 80 is kind of good. It's not ideal, but good. So I also did work on semantic role labeling with annotation projection and sentiment analysis, but since I thought it might be a distraction, so I didn't really include that in the talk, but feel free to ask questions offline. Now I'm going to talk about models about direct transfer. So remember that direct transfer was training directly on annotated data in source languages. The reason that I'm thinking about direct transfer is that in the scenario where we have big amount of parallel data, translation data, the blue bars, like the Europarl data consisting of like about 2 million sentences, we get very good accuracies. But what if we don't have such a big data? So here's the red bar shows the situation where we use just the Bible data, which is roughly 100% small, 100 times smaller than the Europarl data. There's a big drop on accuracy on every language that we have. Meaning that, the supervised model, the density-driven approach with annotation projection is good, but when we decrease the size of the translation data, that is really happening in low resource languages, we can't really get too much of a gain. In direct transfer model, the problem is that when we train on languages, source languages such as English, like I showed the word cloud of English, and we target a language such as German, I show a word cloud of German, the overlap between English words and German words is kind of nothing. They're both Germanic languages. You can think of like English and Arabic. There is no overlap. So that's why people actually back up to part of speech tags as features, so just they ignore the words. And because of this reason, the accuracy of direct transfer models is very bad. So here the gray bar shows the accuracy of direct transfer models compared to accuracy of a annotation projection model, showing that if we remove lexical features, we lose a lot of information, and the direct transfer model is not reliable for us. That's only good when we don't have any translation data. So the idea that I had for this research was that what if we have small translation data such that we could create word representations for tons of languages, such as here it's a word cloud of like Arabic, Hebrew, English, Spanish, French, Portuguese, and so many other languages. And can't we also use that small translation data to bring in lexical translation to the source languages? There are two questions that I wanted to address. First, the lexical representations, and second, the lexical features. The assumption is that we have labeled data set for source languages and part of speech data for all languages, including the target, and large amount of monolingual data. What I mean here is like Wikipedia. We extract very small translation dictionaries, T, W, I, and J, where T, W translate the word W from language I to language J. The way that I extracted such a translation dictionary is by taking the most frequent word alignment from the Giza++ alignments. So what I do here is that since it's a non-neural network parser, it doesn't have embedding features, so I had to work with word clusters, Brown cluster features. The whole notion of Brown cluster features is to have a hierarchy of words where words in the same kind of neighborhood will have roughly the same meaning. Here, apple and pear are both fruits, so their bit string representations are very close to each other, while bought and drawn are verbs, they're in a different neighborhood. The question is, can we come up with a word clustering method that is beyond one language, such as this? So this is a fake, clustering, but it kind of shows what I mean by that. Here's like the word apple, the word apfel and palme are the same meaning of apple. So ideally, we need these kind of words to be in the same neighborhood. And just to remind you that the same idea can be applied if for whatever idea that we have, the same idea can be applied to create cross-lingual word embeddings. So there are a bunch of ways to come up with cross-lingual word representation. I think Walid also had one paper on, I think, massively training on massively parallel data, and I think multilingual data for creating cross-lingual word representations. And most of them are kind of regularizing the words with the same meaning to have very close representations across languages. But I noticed that there is a thing where, these word-to-vec models or word clustering models are based on context. So if I manipulate the context by replacing random words with their translation, such as this, and if I train word-to-vec or Brown clustering algorithm on this, I'm kind of biasing similar words to be in the same context, meaning that ideally at the end I will have similar words with similar word representations. The cool thing about this idea is that I don't have to change any of the objective functions in word-to-vec or the Brown clustering algorithm. And actually, when I did this research, I thought this is novel, and then I noticed that 3 or 4 other papers did the same idea. So it was just very, it's, I think, because of the simplicity of the idea. So then when we have this code switch data, a bunch of sentences in different languages, we can train word-to-vec or Brown clustering algorithm to come up with features. So
how do you decide which words to switch?
Random.
And how do you decide the density of switching?
Just I picked at most 30% of words. Just one number, yeah.
So what's the, how often is the context wrong? Are you focusing on words that are kind of always synonymous? Because certain words have a good translation in one context but not another. So
yeah, given the unsupervised setting that we had and the small data set, we can't really help on this. But that's a really good question. Yeah. So that was about word representations. But for non-neural network models, we also have actual word features that we can use. So I thought, okay, we don't have actual translations, but we have a small translation dictionary that for some words we have translation. Why not bring those words instead of the actual words in translation? Here we see a English sentence in blue, and the green words at the bottom are the words that were in the translation dictionary, so we can bring them to the sentence. So it's again a code switch data where some words belong to the target language, some words belong to the source language. To wrap up with this kind of representation, the way that we did was for part-of-speech tags, if it's a non-neural network, model, we just use part-of-speech binary indicator features. For original words in the source language, we use the word cluster features where it's trained on that setting. And for translated words, we use the actual word features. Going to the neural network model, the same idea. POS translates to POS embedding. Original words translate to fixed pre-trained cross-lingual representations. And the translated words can go for being fine-tuned as the target language word embedding. And the other thing that I did here is the same algorithm that I showed you in the previous slides about annotation projection, is that I added these translated source data set L1S to LSM, to the full trees. So we have now the partial trees plus the full tree from annotations and also the translated data. So here, instead of using monolingual word clusters, we use cross-lingual word clusters as features. So here's a kind of depiction of the 6 languages and their performance. When we use nothing, just a direct transfer model with POS features, here are the accuracies. For some languages, such as Italian, it's magically good, like 79. For some other languages, such as German, it's really bad, 59. When we add cluster features, just cluster features, we didn't really translate anything, we get improvements, slight improvements in German, but good improvements on other languages. And when we do partial translations, we get another kind of improvement. So For example, in Portuguese, we jumped from 77 to 84. And when we add them to the projections and apply the same density-driven approach, we get very good accuracies. For example, in German, there is a 10% jump. In some other languages, there is a slightly less jump, or sometimes the model is saturated, so it doesn't really add too much value to the model. Well, comparing to state-of-the-art models, the left-hand side is the work by Walid. If I'm not mistaken, it's using the Europol data to create cross-lingual word representations, and it's using some language family features in a stack LSTM neural network model. The two right-hand side bars are the same supervised models that I've shown you in the first section. Here, the density-driven approach with the Bible data, as I showed you, doesn't work very well. Interesting. The model that I proposed just now, when just training on the Bible data, gets better accuracy than a state-of-the-art neural model. And I was asked about that. This is a non-neural parser, why it's doing much better than a neural parser. And I have kind of two answers for this. One is that the neural models are kind of fine-tuned, while in an unsupervised setting, it's really hard to fine-tune because we don't have supervision. And second is that this model is really kind of designed for this specific task. And I guess Walid's work was kind of very universal. So the density-driven approach, when it has, Europol data, is really good. But the interesting fact is that when we apply the very same model, but with the Europol data, we get accuracy very close to a supervised parser. So that's a really great thing for us to have such an accuracy. But you might say, the stuff that I've shown up to now was all European languages. They belong to the same family, so we don't have so many of the problems that occur in languages from different families. And I agree with you, that really happens. I ran experiments on the new universal dependency data set. Here are the languages that got accuracy below 70 or around 70% in my best model. The blue bar shows the upper bound as the supervised accuracy. The gray bar shows the density-driven approach, and the red bar shows the direct the model combined with the direct transfer and cross-lingual word representations. The interesting fact is that for some languages, such as Turkish is a morphologically rich language. It's much richer than any language that you can imagine among the famous languages. I only had one full sentence projections from density-driven approach, and that's why the accuracy is like about 18, which is kind of random for us. But combining that with the direct transfer model, I got up to 59.9. But still, there's a big gap to 51.9. There's a big gap to 78.8. The happy news is that one of the bad languages is Persian, which means that it's my native language, so I can work on it to see what the problems are. And I will talk about the problems as well. The next slide shows one interesting thing, which is that these are the languages that are their best accuracy is from 70 to 78. You see that there is this language, Latin, the third one. Its supervised accuracy is less than our accuracy. That's why, because the Latin data set is small, like 1,000 sentences. Kind of, I can claim that if you had some amount of budget to annotate 1,000 sentences or use transfer methods, I will say maybe transfer method is a better approach. Less money, but better accuracy. The other thing is that we are getting very close to a supervised parser in many other languages. The more interesting thing is that for, again, some European languages, our accuracy is more than 80. For all these European languages, and remember that I'm using the Bible data, the smallest setting ever. And the Bible data, if you just take a look at it, it's very archaic. It's kind of out of domain, while the tree banks are news text, Twitter text, web text. So it's kind of very different. But still, we're getting like 86% of accuracy for Italian, or 84 for Slovenian, and for Portuguese, we get 82, and so on. So that's a good indicator for us that we're really doing good on so many languages, while we should address the problems for languages outside the European families, such as Turkish and Persian. I will also give a brief intro to the sentiment analysis system. It's completely the same idea with two differences. The first difference is that I don't, so it's a deep net, so I'm using word embeddings instead of cross-lingual clusters. And I'm using by LSTM features. So here, for a sentence, I do a partial translation. So you see that the word post, I think it's wrongly translated from the Bible to something else. It's translated, to is translated. There was no Facebook at the time of Jesus. So it's just Facebook is not translated. Then it goes to a word embedding layer. It's, again, fixed pre-trained word embeddings plus tunable for the embeddings. And there is an average layer which takes a bag of words average of the embedding layers. And there's an LSTM layer where I get the final representation of the backward and the forward LSTM. All of them are concatenated and fed to a multi-layer perceptron. There is a problem with this model where if the two languages, the source and target languages, have completely different syntactic orderings, LSTM is really sensitive to the syntactic ordering, so it might not do as well as we expect. So here I show the results on the Bible data for 16 languages, except for Persian, it's all Twitter data, and you know what Twitter data is. So if I just pick the neutral baseline, it's a three-way sentiment analysis, meaning that I have positive, neutral, and negative. I get 18 macro average, while projection gives us 40. The direct transfer model with all these fancy stuff gives us 41. And the ensemble of them, meaning that I train direct transfer model per source language and also projection and do the majority voting on the label, I get 42.9. There's a big difference to a supervised model. The main reason is that for languages such as Arabic, Uyghur, and Chinese, we don't really do very good. So there's a big avenue of improvement for the languages that are outside the kind of family of languages. The other thing is that what happens if you had bigger data? For European languages, I had bigger data. So for 10 of the European languages, I ran the experiments with the Europol data, which is contemporary, political, and I had the Bible data. And we see that with all the settings, there is a big improvement by adding more data and contemporary data. So meaning that, yes, the working on the Bible data is good, but if we had more data sets, like more parallel data sets, it's better to make use of them. So now I'm going to talk about the problems that we're facing, the challenges that we're facing with the models that I propose up to here. The first problem, as I said, was most of the models, I think almost all NLP models that I can remember are based on by LSTM or some CNN or some RNN features. So meaning that it's really sensitive to the syntactic order of the languages. So just solely relying on like cross-lingual word embeddings is not good. Because when we do cross-lingual word embeddings, hopefully we are capturing cross-lingual word representations, but how about syntactic, order representations? We're not doing good. Also, embedding language family information is good. I tried that actually. It gives some improvement, but still there's a big gap to a supervised parser. So what should we do? So what I'm thinking now is that instead of doing all this fancy cross-lingual stuff, what if I had a by LSTM model that is trained on some translation data such that the sentences from the same meaning have the same final representations by LSTM? So here I'm thinking about having individual word embedding dictionaries for languages 1 to M, and we do a linear projection to a shared space during training, and after projection, we feed them to a by LSTM, and we hope that this by LSTM representation is the same for all languages. And the way I'm thinking of training them is, we can use noise contrastive estimation objectives to train by LSTM where the final representation of the sentences in translation data should be roughly equal. So I'm in the middle of this process, so unfortunately I don't have any numbers to show to you, but hopefully I can have numbers in a month or so. So as a conclusion, from the time that I started this research, the accuracy of annotation projection and then direct transfer models was not kind of reliable on us. But now I can say that, hey, we can use them. So it's not like unsupervised learning anymore. So in other words, it's not just a fancy abstract research. It's now a practical research problem. But the question is, can we kind of apply this to different domains or different problems, such as instead of looking at different languages, looking at different domains? For example, our data is on news domain, we're targeting medical domain or Twitter domain or blogosphere domain. Or the other way is that can we, for these shared representations that I said, can we train one shared representations for tons of different NLP tasks? So we don't have to do this tedious work of training things for all independent tasks. So these are the things that I think should be addressed, and I should really think about it before wrapping up my research. And thank you for listening to my talk.